so let me get this out of the way. Oh, so let me see if there's anybody asking any questions. No, no questions. Cool. Okay, so let's move on back to our PowerPoint. And let's begin. Where are we? Here we go. Here's where we were. Let's start talking about the beginnings of this subject that we're talking about, quantum theory. Now, it started out with the study of radiation emitted from hot materials. And what we mean by that is essentially, for example, if you cook on an electric stove, you'll notice that the coil, as it gets hotter, it also gets kind of like into an orange, maybe even red kind of color. And so scientists were interested in studying, well, what are the actual frequencies or wavelengths of these radiations that come from metals when they get heated and they cool down, for example. Well, the theory was that electrons were absorbing energy, and electrons had a sort of like a vibration, like a spring, and they would vibrate faster or slower depending on how much energy they had, right? Now, if you studied physics, you have actually probably had at least one lecture where you studied the motion of a mass tied to a spring, a frictionless spring. And what you found was that the vibrations of that mass cover a whole spectrum. In other words, and I don't have a visual here for you, but if you can probably imagine in your mind, get a visual of, let's say you have a piece of metal hanging from a string, and you kind of pull on it and let it vibrate, and you take a camera and take a high speed, a high definition video of it. Then when you look at the video, you can pretty much stop motion that video at every single position that the piece of metal was as it traveled, between the one extreme and the other of the spring vibration. Well, it turns out that when scientists studied these frequencies of objects absorbing energy and emitting light of different colors, it didn't match. They could not find it to go over a continuous spectrum of vibrations. And so along came Max Planck, and he proposed that at the atomic level, perhaps these electrons, they did vibrate, but they did not vibrate over a continuous spectrum of oscillations, but in very discrete positions, all of them products of a single base frequency. And therefore, because of that, the light that was produced by these hot objects was produced by absorption and transmission of electromagnetic radiation in discrete packets. And that's what the word quantum means. It's like a packet. It's like a discrete amount of something, in this case of energy. And to make a long story short, we have what is called Planck's equation that says that the energy of a quantum could be given by the constant h, which has since been called Planck's constant, times the frequency of that particular light. Notice what we say here is, according to this equation, since h is a constant, if the frequency increases, then that means that the energy increases. Remember, we said that, for example, gamma rays have more energy than visible light. Well, if you look back at that chart, you see that gamma rays have much, much greater frequencies, much higher frequencies than visible light. And therefore, these quanta of light carry more energy. Now, Planck's theory was able to explain this, and although it was received with skepticism because it challenged all of the classical physics models of how things move and behave, the proposal was that maybe at the atomic level, matter doesn't behave the same way. Now, along came a very interesting proposal. So this was something called the photoelectric effect. It was something that was very well, observed. It had been observed for a long time. And let me show you what the setup is, okay? We're going to have here on the top, we have pretty much like a little sheet of metal on which we're going to be shining light of a particular frequency. We have the metal separated from another electrode here along a little space there that's it's been evacuated. It's a vacuum in there. There's no particles in there. And then we have that attached to a battery and to a current meter here on this side. So essentially, because of the vacuum between the metal and the other terminal, there is no current. However, when you shine light on this metal, we start seeing the formation of a current. You can see here where the dial is registering that there's a current in there. You can look at the zoom here, the zoom picture here, and you can see that what is happening is the light is transmitting energy and it's causing electrons on the surface of the metal to be ejected. And because there's nothing in between, they travel to the positive terminal because of their charge, and they generate a current. Now, the proposal was, okay, if I make the light brighter, right, I should have more energy, and therefore you should get a stronger current. And the answer was, sometimes you get that, sometimes you don't. The other thing they figured is, well, if I have very dim light, although it doesn't have a lot of energy, over time it'll accumulate, much like when you start heating an object, at the beginning, it takes a little while. Let's say, for example, you have a pot of water, you want to boil it, you turn on the stove, and it takes a little while for the water to actually boil, to get enough energy to be able to boil. And they figure, well, if you shine dim light, you should get a current after a while. There'll be a lag time, but after a while, the electrons will accumulate enough energy to get this. And the answer was, it doesn't happen that way. So along came this guy, Albert Einstein, to explain this so-called photoelectric effect. All right, so let's go here to our makeshift whiteboard here, and let's look at this slide again. All right, so again, notice what we're saying is that according to the proposal, the energy of light is transferred to the electrons and they become ejected right here. The expectation was that if I shine brighter light, more electrons are ejected. That didn't happen. The other one was that if I shine dim light, there'll be a lag time, but after a while, electrons will be ejected when they have enough energy absorbed. It turns out that was a no. As a matter of fact, let me walk you through what were some of the things that were interesting in the photoelectric effect. Okay, so these are the observations. I'm taking time to go through this because back in chapter 2, I skipped all of the history of discoveries that led to the model of the atom. But I feel like this time it's important for us to walk through because I want you to see, how these scientists think and how the process is carried out. And then eventually, how do you prove these things? And I think it's part of our education, part of our process here to kind of like understand more of the scientific process, okay? All right, so here we go. And again, if you have any questions, do one of those hand raising things or unmute your phone or your microphone and let me know if something's not coming across clear, okay? Don't hesitate. All right, here we go. So observation number 1 was that if the light happened to be lower than a particular threshold frequency, you would get no current at all. If you increased the intensity, in other words, the brightness of the light, no current either, even if you irradiate for a long time. So even for a long time. In other words, it didn't matter how long you shone the bright light onto the metal. It didn't matter if you did it, like high intensity or low intensity. All right. All right. Sorry, I think I got a little glitch in the matrix here. This thing is kind of like bugging out on me. Okay, here we go. All right, let's see if we can get this thing to focus. All right. Here was the second thing that was found out. Don't worry, eventually you're gonna get these notes posted on our Canvas page. If the light had an intensity, a frequency that was exactly equal to the threshold frequency, then you got current. If you now increase the intensity of light, remember, intensity meaning the brightness, you get more current. But doing measurements of electricity that you can do, okay, let me see if I can get this a little better focus here. Let me see if I move this. Oh, this is very poor focus here. Sorry, guys. Anyway, you should be able to tell what I'm writing. Maybe I'll have to write bigger here. So if you have increased intensity, you get more current. However, when you do calculations, you find out that the electron, I'm sorry, guys, I know it's kind of like blurry here. And also remember, you have to pin the video screen where I'm doing this, right? You guys pin it? Okay, make sure you pin that video. And I'm sorry, but it's getting very, you know what? Let me get it out of here for a moment. Let me put it back in, see if I can get it to focus. Well, it's even worse now. All right, hold on a second, guys. Let me see if I can work this out a moment here. All right, let's see. Yeah, it's very, very poor here. I'm really sorry about that, guys. And yeah, I'm having a problem with my internet here, apparently. And this thing is totally out of focus. All right, let me do this. Okay, that is not working at all. Let me see if I can zoom in a little better. Keeps getting worse. All righty. Yeah, I know. It looks really weird right now. Well, this hadn't happened before. I've been doing this all week long, and I have not been having this kind of problem. Okay, let me try some more. So it looks like this guy here is not behaving. Okay, let me do this. Let me okay, for those of you watching the recording, just realize we had an issue here with our doc cam, and things were not working very well. So let me wrap this up very quickly here, as quickly as I can. So basically what I was saying was that when you increase the intensity at the threshold frequency, you get more current, but the electrons have the same kinetic energy. These are calculations you can make in physics. In other words, you can measure the current and the voltage and make calculations about the actual energy that the electrons are carrying as they go through that current. All right. Then the last thing that they realized was that if you are at a frequency that is greater than the threshold frequency, of course, you get current. And if you, but also the electrons have more kinetic energy. Now, for us at this point, that is not going to help us much if we're not familiar with some of the principles of classical physics and the study of electromagnetic radiation. So suffice it to say, let me summarize by saying that simply none of these results match the laws of classical physics. It shouldn't be this way. So that's where Einstein came in. So let's look at what Einstein's proposal was. All right. And here is what he proposed. We lost it again. Okay, we're having some glitches. So when we take our break, I'm going to have to work this out a little bit. See if I can make it a little less glitchy. Okay, so don't worry, you'll get these notes later on. Sorry about that. But here was Einstein's proposal. He proposed that light travels in the form of particles. In other words, there's some phenomena that are better explained if we assume that light is actually like a particle. And we can call them photons, all right? Then he also said that there is something called a binding energy. Let's use the Greek letter phi. We love Greek letters in science, don't we? And this would be the minimum energy required to dislodge electrons from the surface of the metal, all right? So the idea is that the photon energy has to be greater than this binding energy. In other words, the energy of the photon must overcome phi in order for electrons to be dislodged, right? So what he said was, well, here's the deal. You have a certain amount of energy from the photon, which is from Planck's constant. So this is of our photon, right? This is from Planck's constant we studied before. And what I was going to do is when that photon essentially hits the electron, it needs to have a certain amount of energy phi, and then some kind of kinetic energy, right? Or if we rearrange this equation, we would say that the kinetic energy of the electron would be the difference between the binding energy, between the energy of the photon minus the binding energy. That's the whole idea. So for example, if the frequency of light that you're hitting the electron with equals exactly phi, then the kinetic energy is going to be 0. So it doesn't matter that you bombard the electrons with more light of this frequency, they're never going to get extra energy because all of the energy transmitted by these photons is simply overcoming the binding energy. It dislodges the electrons, but it doesn't give them any additional kinetic energy, right? So that was the idea. So going back to our little model here and hoping this thing holds up. It's misbehaving again. Again, sorry about that, but don't worry, in your handouts, in your recording, we'll have copies of these things. And I got to find out what is going on with my internet. I was hoping it wouldn't do this. Anyway, so let's see what Einstein was going to say here. All right. So again, the idea here is that sorry. If essentially the frequency of light is less than this threshold, what you're saying is essentially, less than. What you're saying essentially is that the energy that is produced by this photon is less than the binding energy. In other words, this light is not capable of providing sufficient energy to dislodge electrons. Now, you can increase the intensity. In other words, you can send more photons. Right? This is the equivalent of saying, okay, I'm going to send more photons. Not enough, because the key is that they have to overcome that binding energy. And again, I apologize for the blurriness here. Now, let's look at this one here. If the frequency of this light is the same as this threshold, then that means that the energy of this photon is exactly the same as the binding energy. But there is no residual kinetic energy. And so even if you hit the metal with more photons, none of those photons has enough energy to give the electrons a little extra kick so that they will have more kinetic energy. And of course, in this last one here, if the frequency is, greater than the threshold frequency, what you're going to have is you're going to have a residual kinetic energy. In other words, this is going to be positive, and therefore what's going to happen is that now the electrons will have some extra kinetic energy besides simply being dislodged from the metal. All right, guys, sorry about this mess with the electronics here. Let's take a break here. Let me see during the break I can work something out here, see what's going on. And we'll come back in. Give me about 5 minutes only, please. Just give me about 5 minutes. All right. And we'll come back. Like I said, I'm going to have all these things scanned and they'll be available for you as PDFs when I post the recordings. Again, I'm sorry. Let me take a 5-minute break and we'll take it from there. Okay.